Good morning and welcome to our webinar, Pressing Matters. This webinar is presented by Bob Long, Whitmix's Manager of Lab Relations, and me, Bernie Jaroslow, Laboratory Products Manager, and is also NBC approved for one scientific credit. You'll be receiving an email with a link to download the CE test. If you do not receive this email, please contact us at webinar@whitmix.com. And now, Bob Long.
Thank you, Bernie. I'm really thrilled to have this conversation with you. I think it's going to help us both a lot. You have been with Whitmix a relatively shorter amount of time there, but obviously got a lot of experience in the business. But I know that you've learned since you joined us that how much that lean manufacturing is a part of all of our DNA and everything that we do as far as developing products that you're involved with now, evaluating the products that we've got, working on new ideas and how that they can work into our processes that we do and so on, and at the same time then examining it from the standpoint of what value it brings to the dental labs itself then. You know, our whole purpose of lean basically is to make sure that we have the right product in the right condition, in the right place, at the right time, and able to be used then. And to me, that is absolutely essential as far as the pressing goes. The preparation work and everything that takes place prior to the actual pressing operation, as well as the
Oh, I don't know if we should go right ahead. I'm sorry, a little technical.
Yeah, I got a little difficulty here with this, so that we keep everybody intact with this. But basically, using these principles, then, I think, is extremely important as far as every part of that pressing work, both the preparation as well as the finish and so on. And the thing that amazes me as in my travels around and visiting labs is the absolutely myriad of number of products I see and the different types of transactions that I see. So, you know, I need to be better acquainted with what these all are. You know, and I'd like for you to go through with me a little bit what these are and what the differences are and how that they affect in the operation.
Sure, I'll be glad to. Actually, there are quite a few different types of pressing materials around today, and I'm sure each one of them would be best served by the ideal lean manufacturing practices you referred to earlier. Well, first of all, let's start out with feldspathic because, frankly, feldspathic porcelains were the first porcelains used in dentistry. They were developed in the 60s. They became what we call, porcelain for PFMs, for pressing, for fusing to metal, and they're very, very common porcelains. They're among the prettiest porcelains out there. And today with pressing, they're in two different types. The first is the standalone press, so you can see an example of that, Vita PM9. I just picked as one example. And all press to products, if you're pressing to metal, pressing to zirconia, pressing to alumina, those are generally feldspathic materials. And again, they're time proven. Now, lucite reinforced glass ceramics have been around for quite some time too. We're all familiar with most, I think, of these names: Surpress, Finesse, Empress, Authentic. These have been around for quite some time. They are time proven. They're somewhere in the 20-year range in terms of their being around and being accepted as a good-looking, good functioning restoration. But today there's a whole new class of pressed ceramics, and that is the lithium disilicate materials. And of course, we all know them as Emax Press. And that particular one happens to be probably the most popular of all of them. But if you take a look at this list, and this is a very small list that I actually put together a long time ago, this will just give you an idea of the impact that pressing in general has had upon the industry, because there are just a lot of materials out there. And they're great materials. Most of them have been around and are, again, time proven. So that's something that we're pretty, always amazed at, the growing pressing marketplace.
Well, you say that's a small list, and yet that looks like a fairly large list when you think in terms of the lab trying to make the decision is what their skill level sets are, what they have their capabilities, and how they're best going to react to what that doctor's needs are. It seems to me that the idea of some kind of standardization programs and dedicated kind of a regimented program such as Lean would provide will become extremely invaluable as far as making sure that they're giving the doctor exactly what the doctor wants.
I think you're right, and that's why pressing matters, because today it's just growing at an amazing rate. As you see on the slide, there are over 50% of the labs in the U.S. that are now pressing. And this is not outsourcing. These are laboratories that own pressing systems and are providing pressed restorations for their accounts. Now that growth is reflected in the last 3 years as somewhere around 1 out of 5 labs. So that's grown by actually over 20%. So that's pretty significant growth. That tells us something. It tells us that this is a viable restoration. It's a restoration that's desirable, that the dentist wants, and that the patient wants. One of the reasons that it is, and I have to say I'm most thrilled about, is that this is a what you see is what you get kind of technology. Whatever's in wax is duplicated in ceramic. So if you've got ideal margins, for instance, in wax, they're going to be ideal once they're pressed. Under pressure, they come out perfect, as opposed to, say, adding a porcelain margin to some type of a substructure where you have to, a conventional porcelain where you're building in air with the powder into the marginal area, and then it shrinks, and you have to add more and fire again, add more, fire again. This is a whole different and very much easier system, and it works. It works really well. The most important thing is everybody's happy. You know what? Your customer's happy, or the dentist is always happy because he's got restorations he knows will fit, he knows that will function well, and they look really nice. And of course, ultimately, the person we have to please most is the patient, who in virtually 100% of the cases is thrilled by the aesthetics of their restoration. So I think that's probably why pressing really matters.
Well, James Womack in his book on lean thinking, which is kind of the Bible for the lean manufacturing thing, outlined 5 principles. And I think those principles need to be understood and really related to the pressing operations as much as we possibly can. First and foremost, his first principle was value, and that's value in the eyes of the doctor. You and I, it doesn't matter, or the technician, it doesn't matter what our idea of the value is. It's what that doctor is willing to pay for, what he sees he really has to have. So if you've got a whole slew of materials, and you've got a whole different sets of processes that you can use, you've got to be able to select the ones that are giving you the absolute maximum value for the customer, for the doctor, because he's the one that establishes it. Secondly, his second principle is value stream, and that becomes every single task that takes place in this process, from the time it comes from the supply to it goes through to the doctor and he's putting it into the patient's mouth. That's the whole value stream, every single thing about that, and every single task. What we look for in that is we identify those and try to make sure we understand each task, and we are able to duplicate each task each time that we do this then on a repeated basis. The other thing is flow. And what we want to do is to maximize the flow through the whole process, start to finish. Ideally speaking, if we could bring a case in and it never stopped in the lab and it went back out on the other side, that'd be the perfect flow. Obviously, we can't do that in the dental lab. There are stops and things that we have to do, because there's things like investing and waiting times for things to set up and firing times and so on. So all of those are important. Since we can't get perfect flow, we try to go to pull. And pull being then basically that you are going to, as a part of the operation, you're going to pull from the previous operation when you need that. Not have you suddenly decide that I've finished with all this, I'm going to dump it on the next process, and it sits there. So we work for pull, and that works extremely well then in the dental lab on this basis. And finally, then, of course, management takes over, and then we try to manage for perfection. Is what we're trying to do. Outside of establishing value and making sure that we've got value in the eyes of that doctor, the other thing that we try to do is eliminate what we call waste. And waste, and basically there's 7 areas that Lean identifies as waste. First being waiting. We spend an awful lot of time with a case sitting on a cart, sitting there waiting for the next process. And the more that we can eliminate that, the better off we're going to be, both financially as well as far as efficient. The second thing is overproduction. And in overproduction, we always say, well, we don't overproduce because we have no finished goods stocks and all this kind of thing. But we do overproduce. And this pressing is a great example. I mean, we've got the artist out there that's putting 14 different powders onto a coping to make sure that it is exactly the most perfect thing in the world. That doctor probably doesn't need that or want that. And pressing is a wonderful answer for him to get the efficient and acceptable product from that. So, rework, obviously, obviously rework is a waste, and it's an expense, and it means then, because of that too, is that when we talk about the flow, rework means that product now has to move backwards and start back again somewhere along the line, and that becomes extremely expensive, and we try to eliminate that as much as we possibly can. Excess motion is another prime example. I see people all the time fumbling around looking for the right burr, the right tool, and so on and so forth. And obviously that's time wasted, that's energy wasted, that's everything else under the sun that we don't need, or as from a lean standpoint within this. The processing. Processing, one of the biggest ills in this is inspections. I see so many labs going through so many steps of inspection now on this, and you cannot inspect quality into a product. You've got to build it into the product then. So this becomes a redundant kind of thing that doctor is not willing to pay for you to do that, and that becomes a waste. The inventory, your WIP, your work in your process, it becomes the biggest inventory that you have. We take a product, we add some labor to it and some materials, and we let it sit. And we add some more labor and some more materials to it, and we let it sit. And it keeps going down the line, and it gets more expensive and more expensive as it grows, as you add labor and as you add materials to it. So now then, at the end of a 2-week period of time, you've got all of these cases sitting around there, and they build up this huge value. So the quicker we can move those, and quicker we can get this to flow and get it out of there, we can get paid for it and get financially be better off. And then transportation is the last one that we always talk about. And transportation is not your drivers taking it out and everything, although it could be examined from that standpoint too. But transportation as far as within the lab and that movement back and forth from one end of the lab to the other and so on, we have to look at that. So those are all ideas that we try to look at from that. So we're adding value and eliminating the waste. And to do that, there's a lot of lean tools, a lot of tools on it. And we're not going to go on all of that burning here at this time. I don't think that's necessary. I do want to touch on a couple of things, though, because I want to talk about First of all, the standardized work, because I think that that is extremely important, Ben. But I also want to talk about the batch size reduction. We have found, and well, actually true lean says that you're going to deal in a single piece flow, which means you're going to have basically one case at a time moving through there. You know, we really can't get there in the lab. We've worked on this, and it goes back to even John Ness. John Ness, back in his days, rest his soul, but he basically said that, you know, a 5 or 6 case batch would be a perfect size to everybody working. And he did this because of a number of reasons. Because if you discover an error and you have to go back and something has to be done, you can work it back into the flow so much easier. It eliminates the fact that people are going to cherry pick certain cases to work on, this, that, and the other, that some case gets pushed aside constantly then. So if we can work in small batches, we will actually become much more efficient. And as I say, standardized work, I think, is really important. And batch size, let me back up on that just a second, if you don't mind. From a batch size standpoint, if I gave you, I read a book and I thought it was the greatest book in the world. I gave it to you and you asked you to read it, and you pass it along to everybody else in the lab, and they all read it. It's going to take a while for that book to get through the whole lab. Sure. But if I take a book and it's in loose leaf, and I read the first page, and I give you that page, and I read the second, and then pass it to you, and you do the same down the line, you can see how much faster that gets all through the lab itself. That's the idea of the batch size one. So we try to we try to control that as much as we possibly can.
That makes a lot of sense.
By the same token, the standardized work, then, if when you read that one page, you have to put your initials on that to show that you've read that, and then you pass it along and everything. If you've got a standard place that you place your initials, and you do it in the right manner and everything, and everybody else has that also, now that becomes the standardization. Somebody at the very end of this then can look at it and say, yeah, everybody read it, they've got all their initials, everything is fine. It's just a great example of standardized work.
Well, speaking of standardization, I think there's nothing more important than standardizing the actual surface of the tooth that the dentist is going to prepare in order to accommodate a pressed restoration. Now, of course, it's not unlike, let's say, a PFM or any substructure that we're going to build conventional porcelain onto. We have to idealize, follow some basic design tenets of the substructure in order to make sure we can put that porcelain in the right condition so it lasts as long as possible. Now, porcelain is essentially glass, as we all know, but glass is a kind of a funny material. Some people would say glass is pretty weak. You know, it doesn't take much for a baseball to go through a plate glass window, but that's because when a baseball hits that window, it applies tensile forces which put the glass in tension, and the glass breaks very easily. But actually, glass can be quite strong, and that's when it's put into compression. Let me give you an example of this. If I was to clear off everything on this table and just have the plain table and, let's say, that same window pane, and place that pane onto the surface of the table, as long as it's in an intimate contact with the table, it becomes very strong. And if you don't believe me, you and I could get up on that little thin, you know, a few millimeter thick glass.
I'm not sure I can.
Well, I'll help you up there. And we get up to the two of us with our weight. In fact, we can invite any of our listeners, too, to join us. And we could jump up and down on that glass. We could dance even on that glass, although that might be quite embarrassing. But once we do, we're amazed at the fact that as thin as that glass is, as long as it's in compression, it's not going anywhere. It's not breaking, even with all our weight. Now, if I were to take that same thin window pane and slide it out to the edge of the desk and just say hold it in place with one hand, I could probably take my pinky and break it into 1,000,000 pieces. That means I would have taken the glass out of compression and put it into tension, and then it doesn't take very much to break it. So now let's take those very simple, that simple example, and apply those principles to preparations. Well, we have to always apply those principles to substructure design when we're making it, but if it's a standalone pressed restoration, the actual substructure is the tooth itself, and the dentist is the one that's going to have to provide us with those design tenets we talked about in order to put the porcelain or the glass into compression. Now, the only way for them to do that is to make sure they have a really good foundation and resistance to load. You need enough preparation on the sides. You need enough preparation of the right type of preparation at the margin.
So the doctor really has to know what your process is going to be.
Absolutely.
So there has to be that communication and that understanding back and forth right off the bat.
That's correct. That's correct. The dentist needs to understand that this is an all-glass material, and as strong as it is, and it's made to be whatever the flexural strength is, 400 megapascal, whatever it is, it's only strong when it's put into compression, as by the example I just gave. So in terms of the margin, marginal preps always should offer resistance, and therefore the glass is in the vertical direction is put into compression. And that's done by creating a shoulder or a chamfer. And normally we talk about 90 degrees. That's a butt shoulder. That's great. That's fine. In fact, it could also be 100, 110 degrees, a little bit of an angle. That's okay too. But as long as it puts it to compression. Now, in terms of the axial preparation, that's the side wall preparation, we need a minimum number. And that minimum number with all ceramics is 1.5 millimeters. Now, occlusally and incisively, vertically, we need 2 millimeter reduction, but in terms of axial reduction, it should be at least 1.5 millimeters. The reason for that is because, number one, we want to make sure that the porcelain looks good, and we need a certain amount of porcelain in order to copy the shade properly, get the right translucency, etc. But in addition to that, and probably more important, we're looking at making sure that the material functions and stays for a long, long time in service in the mouth. So that preparation actually becomes very critical and should be standardized, and that's what ties into that lean standard. Now, the other thing too is that whenever a dentist prepares for all ceramics, they have to make sure one very important rule: they always make rounded point angles and rounded line angles. The difference, of course, is when you have a pointed line angle, that means a sharp edge. The porcelain is exposed to a cleavage area because it's put into tension. So as I said earlier, we want to keep it in compression and only do that when it's bonded in place by to a rounded line angle or point angle. And of course, the dentist needs to remove undercuts during the preparation. Now, that was all preparation for a standalone all-ceramic restoration, pressed or not. The difference in preparing for that and one that's going to be pressed to a substructure is that though some of those tenets are applied, the thicknesses are a little different because we have to allow for that substructure, whatever it is. So, of course, you know, we're looking at little greater thicknesses. The axial wall thickness should be at least 7/10 of a millimeter. The porcelain veneer needs to be about 2 millimeters in thickness in order to veneer it and look and keep the aesthetics that we're looking for. Otherwise, no sharp edges, that kind of thing is all part of the process itself.
So the preparation work becomes extremely important then on this.
Yes, it is.
And at the same time then, preparing your materials that you've got to actually do the work, I think becomes extremely important. Right. One of the things that we did is that we created a lean rock or a lean stone here that we think is very, very valuable in this pressing operation. It is especially formulated for small batches. You can actually, with lean rock, pull, pin, and trim from that impression then after 15 minutes of time. That then gives you a much, much faster process that you can get to. You're not sitting for a long time with a bench set with this way. But if you're able to do that, if you're able to pull it and pin and trim it, that means a lot of your expansion and a lot of your setting has already taken place. Now you've got a very, very accurate product in a very short amount of time to work with. So it's low expansion. The material is very highly scannable then. And one of the great things about that, as I say, within 45 to 50 minutes, you're going to reach about 85% of all the expansion and everything that you've got. So you're going to be able to work quickly with this on it. And you've got a harder product so that you're abrading on that. And some of this modern-day products have got some real abrading processes to them. So you've got a good product that's going to hold up and not chip and not abrade, and then fit's going to be right all along the line. Preparing that stone and getting it right. Again, I mentioned the fact that we feel very strongly about the fact of using the right equipment in the right condition. We'll talk a little bit more later about our mixing and our dispensing and how that we can get the accuracy and the predictability out of these particular units then.
Okay. So I guess we're ready for waxing. Once we've got the model work done, then we're ready to wax. Well, waxing, of course, is the basis for producing an idealized press restoration. Naturally, what you see is what you get is in full bloom here. Whatever you put into that mold is what you're going to end up with in the ceramic state. So obviously, we want to be careful of how we wax. And of course, the wax itself matters because we want to use waxes that are pure, that don't leave carbons in the molds. Of course, that can discolor our very white-looking two-colored ceramic materials. And one of the best ways to do that is to use a product like one of Whippix's electric waxing instruments, because they're not in flames, there is no carbon buildup, and you get a very nice clean wax. And then we're ready for spruing. Once we're satisfied that we've waxed to a full contour and everything looks good, margins look good, then we're ready to sprue. And now there are some very important rules when it comes to mold fill. So spruing, of course, is a very integral part of that. One of the things we can always say is the bigger the sprue, the better when it comes to glass. Glass is not really like molten alloy. It doesn't flow with the same characteristics as molten alloys. So we want to use, instead of the thinner sprues, the 10-gauge sprues that we normally use for mold fill for alloy, we would prefer an 8 or even 6-gauge sprue. And then that will allow the molten porcelain to fill the mold at the pace that it does, and fully or completely. Now, the next rule is do not taper the connection. And very often we do taper a connection when we attach it to a wax pattern, and the reason for that is we create what essentially is called a venturi, and that is something by constricting the flow of the alloy to increase the speed at which it enters the mold, because a venturi will do that. So that's great when you have a high flow material, low viscosity material like molten alloy, but it's not quite the same with porcelain. So we don't want to inhibit the flow of that porcelain. So therefore, do not taper the connection of the sprue to the wax pattern. Next, don't use plastic sprues. We talked a moment earlier about using waxes that burn out with carbon-free. Well, it's the same thing with plastic. Plastic sprues are made of carbon materials. Those plastics can leave residual carbon in the mold, and that, of course, is something that we don't want with our tooth-colored ceramic materials. Always connect the sprue at about 45 degrees. You've got a little bit of leeway there, 45 to 60 degrees, and that's, of course, to aid in the mold fill by this relatively viscous, honey-like flowing ceramic. Units should be sprued at the same height, again, to maximize that fill. You want to make sure that you attach the sprued to the occlusal or the thickest surface, because that design kind of is exactly the same as the mold fill principles for alloy. You do want to make sure it's the thickest area that gets fed first, and in a decreasing thickness as it goes down to the margins. You can use a couple leads, the big molar patterns, Pontics obviously, that aids in getting that molten glass in there. So double leads are okay. There's some controversy about that, but we haven't seen where that's been a problem. And in fact, I think in many cases it's been a real advantage to do it. And the other thing is you want to make sure you sprue the units from the center of the crucible former. I know that seems a little obvious, but we have seen some mispresses that have been the result of sprues that are connected to a little bit over the top of the crucible former, sort of on the side of it, of the elevated slope. So I think that's something we want to just pay attention to.
Well, Bernie, I would hope that the labs are in fact then documenting these kind of standards and having that ready. That's a huge part of lean, is to having the documentation, as well as having the illustrations available so people from a visual standpoint can see these. That's so important in everything that takes place there, that they have something they can go to. Those standards then give you some measurable criteria that you can use, that in case something goes wrong somewhere along the line. And if you've got that, you're in good shape.
I think most lean labs would have that. Laboratories that are not, we can only hope that they would have some standards in place. So we've waxed up. Now we're ready to weigh the wax, and as you may know, we weigh the wax in order to determine how much glass should be used. We do need a bit of a button on the glass. We want to make sure we have enough of it to fill the mold completely. So essentially, it really boils down to the size of the ingot and the weight. So if you're using 2-gram ingots, there are 2, 3, and even 5-gram ingots out there that are pretty commonly used. The 2-gram ingot perhaps is the most common, and that one requires, if you are greater than half a gram of weight with the waxes, that requires 2 ingots. If you're under a half a gram of weight, then 1 ingot generally suffices. Now, one of the things you can read on the slide, that a tip I put, is that if you are weighing the wax and you're using it for, let's say, a press 2 application, that's press 2 zirconia, singles or bridges, whatever it is, obviously that weight is going to be different when you weigh it all together. Mm-hmm. So you want to make sure that you calculate the weight to the difference between the framework and the wax up itself. So you weigh the framework initially before you actually do the waxing, then you weigh it all together at the end, and whatever the difference is the amount of waxes that's there, of course, and you follow the same principles of higher or lower than approximately half a gram of material.
And then you've got it ready to invest at this point, and it becomes so critical in your procedures and everything else that you use on this, as well as the material. And again, we have created a highly improved FormulaOne product that we think answers a lot of the lean needs. Number one, it becomes a universal. It can be used for any kind of just process that you're using there. I mean, it doesn't matter. It works well with gold, it works well with your alloys, and it certainly works with your pressable ceramics. So your inventory is cut down, the number of SKUs that you're holding is eliminated this way, which becomes a lean process then. It works again and fast. It's got a 15-minute bench set on that thing, so that it gets ready and ready to go. It's got a 30-minute burnout time then that makes it easy and quick and continues this flow process that we want to do on it. So we find that it's got a very, very fine set of particles. It does require, a little additional mixing time over some of the other things, even some of our own other investments. But it gets you a good mix and gets you a very, very smooth product. Then you have less work that you have to do later on as far as any kind of grinding or anything that you have to do as a result. So, in preparing this, though, I think that the important thing, I mentioned earlier that we had a dispenser. We have two dispensers. One of them is the dispenser for the gypsum side of the house, which adds water only then to this. And then we also have the SL, which adds both the special liquid and the water for your investment. Too often we take 3 or 4 envelopes of investment, we cut it off, we dump it in the bowl, and then we carefully weigh out then the water and the liquid and everything for 300 grams. And maybe we didn't get 300 grams in that bowl, but we don't know. With the Aquaspense SL, it's going to calculate it. If there's 270 grams there, it's going to put the exact right amount of ratio of water and special liquid in there for 270 grams, not 300 grams, because otherwise your chemistry is off right off the bat, and you don't want to do that. This gives you that predictability. It gives you that consistency that is so absolutely important in the work that we're doing. So we feel like this is a major portion of your lean operation with that. The BPM2, then once you've got the dispensing, you take it to the BPM2. It's a hands-free mixer. It can do that while somebody else is doing another task, such as cleaning up or whatever happens to be there. You don't have to sit there and hold that, so that that becomes lean operation in itself this way. Secondly, it actually does the premix for you also, so that you and I mean, you might vigorously do a premix, and I might do a very, very slow one. So we've set up different chemistry right off the bat.
Right.
This way you're going to get a consistency. Whatever technician's doing it, it's going to be done the same way, the same speed, same amount of time and everything each time. So you eliminate the fact of having to do it manually. You eliminate the fact that somebody's sitting there holding that all that period of time, and then you get a consistent factor on it. Then. So the BPM tool is a very, very lean tool that we think is extremely important.
I like the fact that you don't have to hold it, and therefore you're able to do other things while that's working.
You can multitask at this point in time.
Right.
When you get ready to invest it then, at that point in time, obviously that becomes important. In the matter that you do that and pour that into your ring and make sure that you get the steady stream, a thin stream in there so that you don't have a lot of bubbles with that. But just as importantly is, I want to call attention to the fact that at the end of that, when you pull that ring, then any defect on that base you remove then, because remember, you're coming down, and if you got a tilt in that ring whatsoever, your pressing is not going to be right. So one of the standards, one of the pieces of documentation that I think is important is that you clean that off, use a knife, don't take it to the grinder, right. Don't take it to the trimmer on the thing, because you may then actually increase your possibilities of having a slant or a cant to this thing that's going to bring you a problem on it. So,
right.
Burnout-wise, it just amazes me that what we see. I'm amazed at how few times anybody really ever checks the burnout calibration and where they're at with it. I've been in a lab not too terribly long ago that was off about 40 degrees on the thing. And when they were having some problems, we sent one of our techs in with me that we looked at it. That's one of the first things we discovered. So if your burnout is off, then you're going to have a problem with it.
Sure.
So we have got to then get that recommended temperatures and get that right and handle that on a right basis. If you put multiple rings in there, you're going to have to check that carefully because of the time-wise that you've got. I mean, it obviously takes up more space, it takes up more heat, it does a lot of things, and it's going to effectively change that. Again, then to avoid short pressing, make sure that it's calibrated, it's right, ready to go.
Okay. No, we're ready to actually do the pressing now. Once everything's burned out properly, the first thing we do once we invert the ring and put it in the pressing furnace, of course, is to place our actual ingot and the plunger itself into the ring. Now, the plunger used to be it would be recommended to be heated or not heated depending upon the type of material being used. And it used to be that you could determine which type of plunger to use just based upon your laboratory's preferences. In fact, the bottom line is we have found that there's quite a difference between the aluminum oxide plungers and those that are made, or known as disposables, made from investment materials. The difference actually is in heat transfer. So there's actually about a 10, and I've heard sometimes 20 degrees Celsius difference between the ALOX or aluminum oxide plungers and the disposables. Disposables are one that transfer heat more efficiently, and it's the ALOX plungers that are heat thieves or heat sinks, as they're called. And that's something to keep in mind, because if in fact you do end up with a bad press, a short press, sometimes all you have to do is think about changing the plunger. Now, if it, sometimes 10 degree, raising to 10 degrees for the press is great, and that's what you want to do, but sometimes you can do that without ever touching the controls of the furnace. You simply change from an aluminum oxide to a disposable plunger, and that can make all the difference. So I would suggest the very first thing when you start getting short presses that you do is examine the actual plunger itself. That can make quite a difference in the heat transfer. And then you're ready, of course, to press. Now, I took a quote from an author named Brad Patrick out of an IDT article back last year. The article was called Porcelain and Pressing Furnaces, and the quote was, "No other tool that ceramics use has a greater effect on the final outcome of a restoration than the porcelain furnace." I think that's even more true when it comes to pressing and pressing furnaces. So you're all aware, I'm sure, that Wibix has been making porcelain furnaces and pressing furnaces for some time now. They're quite popular, and for good reason. They offer a lot of advantages. But since we're talking about lean operations, lean manufacturing principles, and seeing how they in fact apply to the pressing operation, we've taken a look at some of our actual features and seen how they benefit the customer, especially the customer that enjoys a lean manufacturing process. The first thing is that it's a much faster press. There is a much less time spent pressing the ceramic than there is with conventional furnaces, and that's due to something called sense pressing. Now, the new furnace that Wibix has come out with is called a ProPress SP. SP does stand for sense pressing, and that's because, in fact, the furnace senses the mold fill. It knows how much pressure to apply to fill the mold, and once it's filled and there's no more filling necessary, it completely stops or reverses the process and gets that unit ring out of there as quickly as possible. So because it's a much quicker press, it also helps in a number of ways. We'll take a look at that in a few minutes, but the most important thing in terms of it being lean is that it's faster. It also minimizes the reaction layer. The reaction layer that we're all familiar with, especially with lithium disilicate products, that's always there, has to be removed. It's kind of a pain in the neck, but it's something that's part of our process. Well, actually, we've found in many cases when we press with the SP, the reaction layer is so minimized so it's almost not to be there. So you could almost say it minimizes and sometimes it prevents the formation of that reaction layer. That's really important. It allows the pressing of split rings. Now you might think, well, how's that possible? Well, in fact, you're determining whether that ring is split by looking at it as soon as it comes out of the burnout. You invert that into the pressing furnace, and you might at that point decide gee, I don't know if it's worth the risk, because if you're going to be pressing a ring that's already compromised by a split, then the question is, do you go through the process, waste the ingots, and then have to go back to the very beginning, as you mentioned earlier, Bob, about that's not very lean to go
Right.
backwards and start over in the process by re-waxing and all the steps that follow. In the case of the SP furnace, it asks you the question, if you have a split ring, would you prefer a lower pressure to the plunger? And in fact, you can determine that. If you see that it's split and it looks like something you're willing to take a chance on, then you're going to be successful with the SP, where you might not be successful with other conventional furnaces. So you would answer yes, and then the pressure would be backed off to about 40 psi from about a 72 normal pressure for that press. And of course, the slower pressure means it's going to fill the mold a little slower, but you're going to get it filled and you're going to have a successful full press. Now, the reason that we talked a moment ago about reaction layers is because they're formed as a result of the high temperature and the exposure to the investments at that high temperature. The longer the ceramic is molten and at that high temperature and in contact with the investment, the more reaction layer is formed. So in the case of the lower pressure option, of course, there's a compromise there. You push it in slower, it's going to take a little longer, add a little more time to that press program, and that means the formation of the reaction layer may be slightly more. Not even as much as conventional furnaces, but slightly more than when you have the slow or low pressure press. So it's a compromise. On the other hand, look what you've saved in time and money. There's a patented fast cool feature, which means you can get that furnace muffle cooled down to the point where it's ready to receive the next press cycle in literally half the time of conventional furnaces. And that is patented, and it's obviously lean because we're not holding up the process.
Good point.
Yeah.
Good point.
There's a global fuse adjust, which allows you to change temperatures without ever actually touching the controls on the furnace. You're able to literally, without changing the readout, you're able to adjust the temperature up and down for a specific firing. We have all the firing schedules of porcelains, quite a few porcelains in the Master Suite, which is a software program provided with the furnace. And that Master Suite is a CD that has all of the firing parameters for all of the porcelains that you might be using. All you have to do is take that, put it on a thumb drive, and stick it inside of the furnace, and you will instantly populate your furnace with those programs and porcelain programs that you're using right now. And lastly, I have to say, there are very few furnaces that offer what we do in terms of warranty. That is 3 years, which is pretty significant. It shows that we stand behind the furnace because we know it works, and it's had a great history. So that's a really good furnace for pressing. I would never hesitate. Here's some examples of what we talked about, the crack control. You see the picture on the left shows a crack. Now, the question is, do you go ahead and press a mold that's cracked like that? Well, look on the right, and you'll see that that's something that I would probably hesitate to do with a conventional furnace. But those 6 units down at the bottom of that picture were actually pressed out of that ring. And they were just done with a much lower pressure at about 40 degrees with that special feature the SP offers. Couldn't do it otherwise. Now here's something that's pretty crazy, I agree, but there's an Onlay, if you look closely, in the middle of whatever that is, that shape that is there, but it's worked. The Onlay was pressed perfectly. In fact, it was an actual case, and the person doing this just wanted to see whether the SP would really be able to press, since it does sense its mold fill, and wanted to see if it would press properly. It did, and you can see the result right there. Now, of course, when it comes to pressing, we put the ingot in, we put the plunger in. A couple little tips, obviously, black dots always upward, and the reason for that is the plunger's leading edge needs to be the rounded edge. If you don't put it in properly, the plunger will, and you put literally the the sharper edge downward, and that becomes a leading edge, chances are will scrape the sides of the mold and introduce some of that in scraped investment into your actual pressing. So naturally, it's important to orientate the plunger in the right way. And then the other tip that we've found, it's a little strange one, but we like to give some good tips that can ensure consistent quality, is if you're using 2 ingots, that you remove the printing that you see in the top of the ingot. A lot of ingots have the shade and the information, name, etc., on the top of the ingot, and it's probably a good idea to blast those off. And the reason for that is when you got double ingots, you got double the ink, and the ink goes somewhere. It does burn up, but it sometimes leaves a little gray residue, which when you have a two-colored restoration, you just don't want any gray in there at all. Now, when you mispress, and it does happen to all of us on occasion, one of our engineers came up with the 555 rule. May sound somewhat familiar. Has nothing to do with insurances. The 555 rule means if you have a mispress, add 5 degrees and try it again. If the 5 degrees doesn't work, then add 5 minutes with that to that 5 degrees, and you should have a good press. If that doesn't work, then we're looking at adding another 5 degrees in temperature. Now, you should never have to go more than 10 degrees unless your furnace is way out of whack. But 10 degrees is normal, but do it 5 at a time. 5 degrees in temperature, 5 minutes in time, and then an additional 5 degrees in temperature if it's necessary. Because, let's face it, mispresses are a result, or I should say short presses are a result of time and temperature. Another quote from that article by this Brad Patrick is, in the hands of the master ceramist, even a 2 and 3 powder buildup is a thing of beauty. Yet, many ceramists are never able to achieve the aesthetics and vitality these ceramic materials inherently possess. Most often, this is a result of poor furnace calibration. And we find that an awful lot. You can imagine our troubleshooting people receive calls all day long from laboratories who have had either mispresses or misfired porcelains, and a significant amount of the time it's due to the furnace calibration being off. So we, of course, since we make furnaces, also make something called a ProCal, which coincidentally for this first quarter of 2012, happens to be provided free of charge when laboratories purchase the SP furnace. But this ProCal not only checks the calibration and says yes, you're off, or yes, you're okay, but it does recalibrate the furnace itself. So you can do that in a hot muffle, you can do it in a cool muffle, you can do a QC quick check, which is just letting you know how much it's off, if it's off at all, without calibrating. But it does work, and it works really well for any of the Pro furnaces. If you use the Pro, if you happen to have a Pro 100 furnace, which was the first group of the Pro series, then it will check the calibration and tell you whether you're off and by how much, but it won't calibrate it. It's only in the 200 series and the SP that it does actually calibrate.
Most important thing, though, is you're checking it for a calibration on a regular basis, because I don't care whose furnace it is or what it is, furnaces are going to lose their calibration over a period of time. And getting this right is so extremely important that I feel like that it's one of the most valuable tools you can have. Again, having the right materials in the right place at the right time in the right condition, ready and able to use. And if that furnace is out of calibration, it is not ready and able to use. You've got to have it right to go with. So,
thank you. That's a good point. So if by chance you do get a reaction layer, of course the reaction layers that are present on the lithium disilicate materials can be removed very easily. And in fact, we always recommend that you do use Ivoclar's Invex liquid. That's an acid that will remove it in an ultrasonic, and it works great. The one thing you don't want to do is blast it and not use the liquid. You can blast following the liquid, but you always want to make sure you use the Invex, because it does really remove 100% of that surface. So So that's something we recommend, even though it's not necessarily a Whitmix product. It's something that we feel pretty strongly about.
Once once you've got it done and it's out of the way, then the natural tendencies, it seems to me, that with the labs that I've visited and everything, is to look for shortcuts on divesting. What we can possibly do, either using some kind of a tool, a burr, or something else. Nobody wants to stand there and do the divesting. It's a boring job. It's not a rewarding job in any way, shape, or form. So too often they will actually take it to a trimmer. They'll cut the top off, the sides off, and everything else. They'll get it down to the point where they think they can, in fact, then start blasting it with a little heavier and then back it down as they go along. And inevitably what you're going to do is you're going to take a chance then of harming your margins and stuff on that. As a result, we came up then with what I think is one of the finest pieces of gear that we have ever produced, and that's called the Excavator. It is an automatic divester. It's designed so that you can take a ring directly from that oven. You can bring it over, place it in there. It will come on in a few minutes, automatically start and divest it unattended with not any technician standing there, and completely divest it down to the point where you probably got about 30 seconds or so of final cutoff work to cut the button off and get it ready to go. It saves time. It means that you've got a ring available to you in about 15 minutes time, even with the cooling period that it does, ready to go, that you're normally going to sit and wait 60 minutes for. So the time savings is tremendous on that. Basically, and then on top of which, not only is it an unintended operation, then it also means that you don't have a technician standing over that, breathing those fumes at all times, and breathing that leaking dust that comes out of there. Mary Borg from SafeLink has commented tremendously on the need for products such as this, because no one seems to be wearing masks. No one seems to be doing this properly before, and she said this is one thing that really, really helps on this. And so this is probably one of the leanest products that we have, and I think it can certainly then give you a much more efficient product in the long run than you have otherwise.
Okay, we're ready to cut. We've divested. We're ready to cut off the screws. We do that normally. There's only one or two things that I would talk to you about, and that is to make sure that you don't apply excess heat when you're cutting off the screws or shaping the units themselves. Certainly, with any porcelain, you want to avoid high temperatures. If you're pressing to a zirconia coping, for instance, that heat is transferred to the zirconia, and that can be a problem. So you definitely want to make sure that you go gentle when you're removing the restorations from the screws. And there are even some laboratories that use water to cool it as they're cutting the screws or finishing the surface. If you do that, that's fine, but just make sure that you don't apply excess heat. That's the only caveat when it comes to screw removal and finishing. And ultimately, you come out, there's the bridge that we saw earlier, come out with a pretty material. In fact, one of the great things about pressed restorations is that they really are aesthetically pleasing to us, as technicians, to the dentist, and of course, ultimately to the patient. This is an example of a case that was done, a 6-unit case done by Bill Morozic. Some of you may know him from the Morozic Prosthodontics. And you can see not only do they look natural and very pretty, and there's a lot of depth there, but they also match the shade really beautifully. So that's the kind of thing you can expect out of pressing if you follow the tenets we talked about earlier. Now, Bill has been kind enough to send me some slides, and I've included one. I like to include tips, as you see, and I've included one tip that I thought was really pretty cool, and most of us would really appreciate this. You know, sometimes it's hard removing an inlay especially, but even sometimes an onlay, depending on how many cusps are there. Once you build it up, but you haven't fired it yet, you got to remove it to, of course, put it in the furnace. And one of the things that Bill does that I thought was great is he actually puts a hole on. If you look on the left picture, you'll see a hole in the side of the model that's angled up, and on the right picture, you'll see that the hole comes through to the floor of the prep. Well, it's just covered with wax, filled in with wax, and in fact, later on, once you've finished the buildup on that inlay or onlay, you just take an instrument, a round instrument, and just push it up, and then you're ready to place on the sagger tray for firing. I thought that was a clever little tip. It saves a lot of time and probably a lot of frustration for most of us. And there's that inlay that was you saw a moment ago in those pictures, and it's looking pretty good to me. Well, there's the inlay in place in the mouth, and of course, pressing gives us those kind of results routinely if we follow the basic principles, and we also add the lean principles in with that as well. Now, we have received a couple questions, and I'm just going to answer those quickly. One of them is that I keep hearing that you can only use a certain furnace to press lithium disilicate. Can you shed some light on that for me? And yes, I can. In fact, that is not true. Most pressing furnaces will work properly with any pressing material, including lithium disilicate. You do not have to use a specific furnace. Our customers have been pressing Emax for quite some time, since it's come out really very successfully, and have never had problems with it. So obviously you have to follow the proper parameters, and once you do, you should be fine. Question number 2 is, how does the furnace detect a split ring? Well, actually the furnace doesn't detect a split ring, you do. There are furnaces, and I know Autoclar's newest furnaces will tell you if a ring is split, then it just stops, basically stops the whole pressing process, basically, because of the split. Then you have to start over anyway, so it doesn't really buy you much. In this case, our furnace is able to, once you detect the split by eye, once you see the split, it's going to allow you to press it or make a decision to press it at a lower pressure, and thereby ensuring a complete fill and a successful pressing. And then lastly, what about using a surfactant when investing? You know, that's something that each manufacturer will recommend or not, depending on the manufacturer. I have seen no problem as long as it's an alcohol-based rather than an oil-based lubricant or surfactant, because obviously we want to remove all of that material before it's invested, and that investment is pressed to with ceramic. So alcohol-based ones, we see no problem whatsoever. I don't think there are any more questions, so I'd like to thank you, Bob, for sharing your knowledge with us, and I think it was a good session. I would like to thank those of you on the phone for joining us in our webinar as well. It will be up on the web very soon. Thank you.